give the talk at the same time.
In parallel.
1, 2, 3. So, yeah. All right, so this one's going to focus on the attacks that seem to be most effective against NIST post-quantum crypto candidates that are based on lattices. There's, of course, lots of general reasons to care about doing algorithm analysis, but I think for this audience, don't really need to advertise analysis as an important thing, especially analysis of cryptographic systems, where if you analyze the cost of algorithms to attack those systems, then you're providing advice to designers of the systems and to users of those systems. But for us, we just care about, we want to know how fast the algorithms are because it's intellectually challenging. So the algorithms that we're talking about are algorithms to break various lattice problems. I should say in terms of credits, the stuff we're going to talk about is based heavily on a survey and a Sage script from a 2019 document, which is from us and from Chichenokchung Satyansup and Christina van Vredendal.
All right, so if you want to have any concrete parameters, so if you want to have like a crypto system in mind to break it, then you can think of the submission that this is from. So that's the Streamline Entry Prime document. This is our middle security level where we're going for this ring up there. So these are polynomials of degree less than 761 with coefficients modulo this q. And then whenever there's something showing up which is low weight, then low weight means, well, weight 286. So the targets for the attacker are to find some A which is in this ring, and not just low weight, but it's even that all coefficients are in 0, plus, and minus 1. So it is small in each of the entries, and there are only 786 of those. We can start writing. That's why we're giving the talk together. Very great. Only 286 of those are set. And so then problem 1 is that you are, as an attacker, given a public element from this ring. It is in this ring modulo q, so the entries are between, well, either 0 and 4,590, or you can go symmetric around 0. And you know that there is another small element e. This time the weight is not restricted, but each of the coefficients is between +1, 0, and -1, and that gives 0. So that is problem 1 that the attacker faces. And we're going to show on the next slides how this relates to some of the crypto systems. Now Dan has to multitask and also talk.
Uh-oh. Write and talk at the same time. Yeah, so problem number 2 is you're also trying to find this small weight W secret A in the ring, and you're, again, given some big G in the ring modulo Q, and you're given that modulo Q, you have AG plus E is, well, something. It's no longer required to be 0. There's, again, some small secret E beyond the A that you're trying to find. You're given AG plus E, but again, this problem 1 is only the special case that AG plus E equals 0.
All right, so if you can break problem 2, well, then you also can break problem 1. And then there's also problem 3, which appears naturally in some of the systems, which is basically just like you're seeing multiple outputs of problem 2 is one way of seeing it. So both of these have the same A, different G's, and then different small vectors E1 and E2. Now, it might be just several of these problem 2 statements, or it might be that they have different distributions. So it really depends on the situation, which system we're attacking, whether these all follow the same level of smallness. But the one thing you know is it's the same A.
And just if you're curious about how much we can prove about the relationship between these problems and try to compress them down to just one problem, why do we have 3 different problems to begin with, then, well, problem 2, as Tanja mentioned, gives you a solution to problem 1 if you can solve problem 2 all the time. On the other hand, if you can only solve problem 2, say, 99% of the time for some distribution of A's and G's and E's that somebody tells you, that doesn't mean that you could solve it for problem 1. Maybe problem 1 is more secure than problem 2. Well, okay, the attacks we'll see later, they seem like basically the same problem. Problem 2 versus problem 3, maybe there's a closer relationship. If you can solve problem 2 for whatever distribution of A, G's, and E's, then you can solve problem 3 for that distribution. If you just forget about the G2 and E2, then you have an example of problem 2.
Or forget about the other one, whichever is closer to your problem 2.
Yeah.
Okay, so then I promised that this would be related to some of the crypto systems. So Entru, or our Streamline Entru Prime submission, what you're given is, well, this equation up there in problem 1 with a 0, it's an approximation, so it's AG plus E equals something, and for n true, this is just 0. That makes it problem 1. And the G, the public value given, is the fraction of two small entries. So A is the thing which is small and controlled in weight, and E is the one which is just small. And then you're given, well, okay, there's a minus sign here, who cares? But it's a fraction of those two things.
All right, another example where you have the same kind of approximation, A to some multiple of this G, where you also know what the G is cryptosystems that are, this is maybe a little confusing because there's a ring LWE problem. There's also a ring LWE crypto system, and in that crypto system, the public keys are, well, two parts. You're given some random G, and you're given some approximation to AG, well, little a times G. You're given a big A. It's another part of your public key. That's little a times big G plus E, which, I mean, you're also given that up here. The difference is that the G in this system is chosen randomly, whereas before, the AG plus E was required to be 0, which limits your choices. We are going to use some different names for these systems to avoid confusion with the ring LWE problem and to emphasize the overlap in, for example, the ciphertext and the structure of this AG equation that you're given. We're going to use an n-true name for both of these systems, where the distinction between the systems will be, well, what you see in the computations here, there's a quotient for that first system and a product for the second one. So from now on, it'll be quotient n-true for the first system, product n-true for the second. And then in the quotient n-true system, if you want to encrypt it, simply do the following. You're given as input some small ring element B, some small ring element D, and then you simply multiply, well, there's some factor 3, which if you exercise, decrypt, then you'll see why the 3 is there. You multiply, basically you multiply G by B, ignoring the 3. All right, then you multiply by 3, then add D, and that gives you some B, which is your ciphertext. And you can see here, just to relate this to the problems, you can see here that the problem of if G were random, which, well, it's not exactly, but if G were random in this, then finding the little b given this big random multiple of b plus some little thing, well, that looks a lot like problem 2 here. You're given some approximation to a multiple of some secret thing, and you're given what the multiplier is, and you're trying to find the little b. So figuring out a ciphertext if the key were random, that would be an example of this problem 2.
Okay, so now we've seen problem 1, once in the public key, so secret key recovery in n-true, problem 2 in the secret key recovery in the product n-true, and in the decryption or in the attack on the messages in the n-true system, the quotient n-true, and then problem 3 naturally appears in the encryption for product n-true, or ring LWE. So you're having, as a public key, you're having a noisy multiple of some AG plus E sitting around there, and then the ciphertext, you're getting a similar one sent over. So the sender also gives you a B, which is small, and a D, and it also takes the same B on your public key, on this A over there, plus C. Okay, then there's also some message. Now, if you can solve problem 3 over there, and we ignore the message, then problem 3 is exactly this thing. So distinguishing or finding B and C and B and D here from these samples. And this is an example where they follow different distributions. Because, I mean, the A is different from the G. So that's a G1, this is the G2 over here. And then if you can get that value, well, then you have the ciphertext without the M. You subtract, and you're getting the message.
For people who want to prove stuff, if you want to formally define what these problems are, you have to start distinguishing between the search version of problem 3 and the distinguishing version, and similarly for problem 2 and problem 1. And then eventually you start being able to prove something relating the crypto systems to some sufficiently tedious versions of these problems. But for this attack talk, this will be enough diversity in these problems.
Okay. So on the next slides, I'm stealing shamelessly from a paper that Dan wrote, and I'm feeling a little bit like when you're in class and the kids ask you, hey, is everything going to be on the exam? And you say, yes, everything that was on the slides will be on the exam. And there's 4 more of those. I'm not going to read out any of this, but this is an attempt, or successful attempt because it's his, I can say that, to squeeze all the lattice-based systems from the NIST competition into this framework. So saying, okay, is this product or quotient? What are the parameters? Where do we live? So where do these polynomials live? So what ring we have, or what module do we have? And then on the following slides, so this will scroll over, in every line is one system. And so then what does short mean? So streamline intro prime, that was our example, this line here. So we're living in this ring. So that was the Q, this was the length. And then over here, short means these coefficients, that weight. And then for all the other ones, we have slightly different notions of what short and what small means. So if you ever feel like, okay, you can solve problem 2 or 3, or you have a new idea and you want to figure out how to quickly map your targets, go to that paper and find this table there. Or go to the slides and find the tables as well. And then some of those have entries such as not applicable, depending what's a CAM, what's an encryption system. Some are working with rounding, some are using problem 1 and 2, and some are using 2 and 3, so there are some differences there. And yes, it's all going to be on the exam.
The good thing is that once you've seen a few of these problems, then you rapidly begin to get used to all of them from an attack perspective. So let's look at how we can actually start breaking some of these systems. Just to again emphasize, this talk is about the attacks that seem to be the best that people know, well, what's called primal attacks against these lattice systems. For the people who were there at the Lattice boot camp, you heard an introduction to primal attacks, and that'll be fitting within the framework, but we're going to cover more of the attacks in this talk. Typically, people describe these primal attacks as, well, there's a bunch of subroutines. At the top, you define some lattice based on the system or one of these problems, or more precisely, the exact crypto system you're trying to break. And then, well, once you've set up your lattice, then you apply, say, BKZ beta, some approximate SVP algorithm, which is internally using some SVP algorithm, and then all of this is based on some model of computation. This talk is not going to be about the low layers here, although my next slide will be one slide about models of computation. We are going to focus primarily at what's going on at the top here, especially how you choose lattices and how that interacts with the cost of approximate SVP. Maybe I should also mention, when you really optimize these things, you start seeing the layers are not exactly described by typical statements of the approximate SVP. You shouldn't think about this layering as some straitjacket in how you're designing or analyzing algorithms. There can be interactions between the different layers. All right, so briefly, one slide about models of computation, which really affects everything else. And really, I mean, it's not just that it changes the exact numbers of costs of things. It'll often tell you some algorithms are better than others, where you thought from a different model of computation that the other algorithm was better. And so you really have to be careful about what your definitions are. And also, when you're talking to users who are worried about attackers who have some real model, you have to worry whether your model is actually describing what the attacker can do. Typically, for theoretical computer science, we'll start with, say, a multi-tape Turing machine as a model of computation. Or maybe a single tape, but single tape is like too wimpy, it's too slow. It takes n squared time for lots of things where you feel like, wait, I can do that in linear time. Like sorting. While a multi-tape Turing machine, if you have n integers, just as an example of how fast this is, I'm not going to give the formal definitions, but just to remind you of the resulting speeds, multi-tape Turing machines feel kind of realistic. If you want to sort n numbers and each number is kind of small, the total time you need is basically n. I'm suppressing as n to the 1 plus little of 1. I'm suppressing things like log factors. And then the space you need, of course, just to write down the integers is n to the 1, but also that's the total space for your computation. Well, in that amount of time, you wouldn't be able to get farther than that on your tapes. These days, in an era of climate change, we're also supposed to worry about the energy cost of our machines. And before we get to the 2D circuits, let me just say on the multi-tape Turing machines, if you have a single tape, then you can have your data sitting there, and the head of your machine is moving along, like one little energy unit for each time step. But as soon as you have two tapes, you can't do that anymore. You need energy to move your tapes, and that energy is linear in your tape lengths. On every step, you need time n to move your tapes of length n. So your energy cost here is actually the product of the time and the space. You have n squared energy. And then people started... I'm sorry?
If one of the tape is moving...
That's right, yeah. Yeah. there is actually an interesting, if we ignore issues of friction and stuff, then yeah, there is an interesting section in Knuth's Art of Computer Programming about sorting on tapes. And one of the issues there is like when you've got tapes moving, then same thing for disks to some extent. When you've got tapes moving, then it's good to read serially. So you have something having that momentum. That is a physical effect, which you do notice. Nevertheless, if you build bigger and bigger, if you imagine n being not just 2 to the 20, but 2 to the 50, 2 to the 100, you start seeing linear effects from things like friction and tape tension. Okay, also, I mean, even a laser doesn't, never mind. All right, so moving on to, people started thinking in the 70s and 80s already about ways to model computation which would use the hardware that you have available more efficiently and use your energy more efficiently. I mean, if you have 2 to the 50, 2 to the 100 units of storage, and one little CPU core sitting there talking to that storage, that doesn't make sense compared to buy billions of CPUs. It's not going to significantly add to your cost. And well, Brent and Kung said, all right, computation is done on a big square array of transistors connected by wires. Sounds kind of realistic because, well, that's how we do computations. Maybe not once we have quantum computers. I mean, you can say, hey, this is still not the end of the story. But I mean, they said, all right, they said this is not just reality, it's also a good theoretical definition. And they started proving theorems about it, like the AT squared is n squared theorem for integer multiplication of n bits, or for sorting, which is equivalent, that you can get your sorting time down to sort of the distance across your chip times some small constant. And your space, of course, for representing n numbers is, again, n to the 1. Your energy cost looks like n to the 1.5, which is much, much better than n squared. And this is actually achieved. When people do sorting records and measure the time and energy, it really does follow this curve, and you can pinpoint what the little O ones look like. It's not just some obscure asymptotic result. This is reality of sorting today on big clusters.
What's the energy?
I'm sorry?
The energy cannot be n square root of n.
The energy is n to the 1.5. So it's, yeah, like each spot in your chip is using some energy at each time unit. Okay. You could say, hey, we can get even better, get down from, instead of a square root speed up, let's get some exponential, get down to polylog time for sorting if there's polylog bits in each integer, using a PRAM. Now, okay, you have to be precise if you want to prove theorems about PRAM, say what exactly that means. And the definition's an interesting thing that happened in the transition from Turing trying to model physical computation. The development, when it got to PRAMs, also in the late 70s, early 80s, the definitions stopped having arguments that they were physical, like this is something you can actually implement. And if you imagine what it would take to sort 2 to the 100 items, we could barely imagine storing those. But if you imagine sorting 2 to the 100 items in time almost constant, that doesn't make any physical sense. But, well, you can still define this, and you can analyze this, and lots of people do analyze algorithms in a PRAM. And then you can do all this again for quantum computers. So for quantum computers, people have defined, for instance, you can define quantum 2D circuits, which are more powerful as far as we can tell than normal 2D circuits. And you can define some more parallel quantum things or less parallel quantum things. And you must get these definitions right if you want to do serious algorithm analysis of lattice attacks.
All right, so lattices. I mean, this talk is about lattices, so how do we get from the problems 1 to 3 that we have on the board conveniently for eternity to anything looking like a lattice? So we're trying to find something which is short, and reminding you, so A was the short thing with fixed weight, E was a general short thing. And so for these, it doesn't actually matter that they're mod Q, because, I mean, they're just 0 plus minus 1. For the G, it does matter, and for the solution we're given here, okay, for problem 1, it's 0, but this is also a statement in our mod Q. Then, as always, is problem 2.
All right, so problem 2, the difficulty here is this word homogeneous. I mean, problem 1 was given as a homogeneous equation, AG plus E equals 0. But for problem 2, we're given, you'd want to say, well, find an A and an E, which have AG plus E equal to this other thing we're given, but that's not homogeneous. It's inhomogeneous. So clever mathematics here, you homogenize, put in an extra variable, so now you've got a homogeneous equation, which, I mean, the solution you're looking for, of course, is the short A, short E, and T equals 1.
All right, and then for problem 3, once we mastered problem 2, it's again the same, so we stuffing in the T1, same as here, and this T2 here. So if you have an inhomogeneous system, if it's not equal to 0, you homogenize it by adding an extra variable. So here we're just in R2 for our solution. Here we are R3, where the one variable comes from having this t extra. And here we're now down to R5. Then turning this into lattice. So we basically have in this map there that we turn a vector a comma r into this vector. And so what happens is that the first part, so we're mapping our a bar and r bar times a 2 by 2 matrix. And then the first one is just the identity. So we have in the first quadrant here, we have I, and the r doesn't get used at all, so there's a 0 here. And then the second part, we have q times r, so we're having a q times identity matrix here. And we have a minus a times g, so we have this g thing now written as a matrix. So there's one step in there how we turn from the rings that we have over there into matrices. And so what we have there is a polynomial multiplication with the reduction, in this case, modulus polynomial of degree 761. And in general, you have your structure, either it's cyclotomic or it's like with a plus in the middle. And so you can always write this as a matrix multiplication where you have basically the polynomial times the first row is the constant term, then the x term, x squared, and so on until x to the n minus x to the degree minus 1. Okay, and then you have your nice lattice here. And thanks to Alice, we already have seen how to deal with lattices, well, which are actually modules, because these are elements over R.
It's time for problem 2. So problem 2, well, you do the same thing where you're thinking of that the E that you're looking for in the end, that's supposed to be modulo Q. It's supposed to be the secret A times G plus E, minus AT, that's supposed to be E in the final thing. And here, this is no more mod Q. We have to explicitly say what that extra variable is. So, okay, the image of this map is exactly the, of course, to define this, you have to lift G, like Tanja was mentioning, takes, say, between 0 and Q minus 1 for all the coefficients, lift G from R mod Q to R, and then this map has image exactly the solutions to this equation modulo Q, and then you're just trying to find a short vector in that lattice of rank 3 times the degree.
Okay, and then problem 3, just the same, just going up from 3 variables to 5 variables, again, putting in the Q's to do the lifting, and everything stays the same. Now, how do you break these? And Dan was already referring to Martin's talk from the boot camp, and I was referring to Alice's talk this morning. So we have these R modules, and can look at them as lattices, but we have some extra structure here. So we can use this extra structure to find not just one solution, because we do know that this A comma E or this A T and E and so on, depending which problem you're looking at, we know that there is at least one short solution. But once you have one short solution, because of the algebraic structure in here, you're getting lots of independent short vectors. For instance, for the problem 2, we have this short vector. But if you multiply by x, okay, for the normal n-true lattice where you're computing modulus cyclotomic polynomial, or with x to the p plus 1 minus 1, you're basically just shifting around. So this has the same weight as this one. For n-true prime, it's a little bit worse, because at some point you're reaching the degree 761, and then you're turning the x to the 761 into x plus 1 instead of just 1. So the degree goes up a little bit, but it's still very short. And then you multiply by x squared, and you're getting, for each of those, you're getting a short vector. Or you can do linear combinations of those. For instance, you can take times, yeah, those didn't make it on the board before, right?
Sorry.
You can also do like linear combinations. You can take the original vector plus this vector, also known as you multiply by x plus 1, and so you get another short vector. So these give you fairly short combinations, and so just by knowing that there's one, finding one of them gives you a solution, and also for the attacks, it doesn't really matter which one you find. So if you're finding this as your short solution, that is equivalent in the breaking to that one. For instance, if you're looking at the fractional as a quotient n-true, the x just falls out, and else you're getting everything scaled back. Question, yes?
This is an artifact of how you homogenize the problem. Like if you had homogenized it by just adding a 1 instead of an entire ring element.
Gonna get to that.
That wouldn't be homogeneous over R. So these,
Yeah, but I mean, at the moment, we're still living over R, so every extra variable you introduce gives you an extra variable over R.
Yeah,
And so the natural homogenization gives you this thing. We get to bi-Galbraith in a moment, if that's what you're thinking about. We get into bi-Galbraith in a moment if you're thinking about that one.
I wasn't thinking of that. I'm just saying this is just the artifact of the particular homogenization that
Sure, you can throw away solutions if you choose to. But, I mean, they all exist.
after you've homogenized it in this way.
Yeah. I mean, on the way to a lattice, you homogenize, and this is a recus, a module over R, so this is the natural way of homogenization. So, throwing away knowledge is often a good idea. So there's a paper by Alex May and Joe Silverman in order to reduce the degree or reduce the dimension, because all the lattice attacks that are not topic of this talk, but of course we have to live with the larger the dimension of our lattice, the longer these attacks or the longer these algorithms takes. And so it's often a good idea to put some of the variables to 0. In particular, in our A over there, we know that A is small and very restricted in weight. Out of all the 761 positions, only 286 are non-zero. So the weight is very, very low. And so it's a good idea to say, hey, we're putting some of them to 0. The rank will go down. So it's going to be smaller by exactly that number which we're fixing. And so the lattice will be faster. Of course, we might have been wrong in that. Maybe one of those positions was not 0. So it's a question whether it's always a speed up. And, well, that just means if it's not a speed up, you have to check where your parameters are living. Probably this one number I give you next is not always the right one. But for instance, here, I have a 13 on the next slide with exact numbers, which looks good here. But it also is a function not just of the length, but also of the size of Q. And then
Canon is when you don't know that the secret is small. So that would be like you didn't restrict A to be small. And then you take 2 samples, and then you basically convert into 1 and do by Galbraith. That gives you the Canon embedding.
All right. So since I had mentioned by Galbraith already, so what they are doing is basically going the same direction as Chris mentioned in his question. You're looking at this thing, say with problem 2s, you have a lattice. So you're starting with R to the 3. So you're having this 3 dimensions over R, so 3 times 761. And then he says, well, we're forcing many of the positions of A to 0, so same as my Silverman, and most of the positions of T to 0. So many that only T has degree 1, is constant, so T equals 1. So that basically removes this homogenization. It's no longer homogeneous over R, it is homogeneous over Z. And so it's a valid step, but it is reducing a lot from 761 to just 1. That is nice for the dimension of your lattice, but it also removes a lot of the symmetries. And the symmetries can be nice because all of those solutions were there, and suddenly by this one choice, they're all gone. So again, same question, is this always faster? Definitely, it looks like if the Q gets large, there's another question to answer. But by Galbraith naturally fits into the system, basically as a specialization of my Silverman's idea. All right, so standard analysis, as I already promised. Let's look at some concrete numbers. So now we're back to the problem 1 for the streamline into prime. So our 761 lattice, weight, well, 268, not 269, 86, not 9, so it's almost square of 17. And then just problem 1. So we have 2 times the degree of the polynomial, so 2 times 761 as a dimension of this lattice, and then we're going to apply the my Silverman idea to this, and we're going to force some positions to 0. Now our E, that was not restricted in weight, it was just restricted in size. So basically, 2/3 are going to be plus or minus 1, and 1/3 is going to be 0. So if I look at the Euclidean norm, then it's probably about square root of that, so about 23 of that. But that's just taking the average value. And we don't know. I mean, the E is randomly chosen. It can be more extreme on the larger side or on the smaller side. And then will it change the security analysis to do fixed rate for this, which Entro initially did? In Streamline Entro Prime, we're saying, well, we're taking a larger solution space or larger problem space, and so we don't restrict this. But that also means that we're looking at a different distribution. So, I mean, we didn't email those in for the open problem session, but we have lots of open problems on the slides.
In general, if people are reading the slides, the parenthetical comments you see, basically each parenthetical comment is at least one open question.
And sometimes contradicting questions. Like, what is smaller, what is larger? We really, I mean, this is an open question which we are interested in seeing. And yeah, now I spot you. So if you're taking notes, or we can just, I mean, we'll have the slides online afterwards. Okay, so in my experiment, we're supposed to put some of the variables to 0. Say, for instance, we're putting 13 variables to 0. That means out of the 761 choose 286. We now have, well, only 761 minus 13, and then choose 269. And so the fraction of those two is a probability of 0.2%. That means forcing those 13 positions to be 0 has reduced our chance that this actually finds it, because, well, these 13 might have been having at least one which is not 0. On the other hand, our rank is much smaller. The degree is much smaller. We're down from 1,522 to 1,509. So then it depends on the speed of the lattice attack whether this is an improvement or not. And if not, well, this is the parameter to change. I mean, if it was too many, if it was too few, you can play with the probability. If you have a very fast lattice attack, I mean, in Elsa's talk, there was like, let's assume we can magically solve CVP. This is not a good thing. I mean, if you can solve SVP, CVP, then you're done. You don't need this. But if you have a realistic cost, you can tune with this parameter. And as I said already, the attacker is also happy to get rotations of this or multiplications by x. So any of the short ones are fine. For the quotient ones, the x will just fall out. And else, well, you will probably notice with something that you have a multiplication by x sitting around. So the standard analysis, so you have this probability of the 0.2% of being in this lattice where you have forced some of the positions to be 0. And then can we just repeat this with different choices? Do we just get, we have tried this 5 times, do we now get 1% probability? Let's just assume that they are, but in this case it's less a question, it's more like a comment. They're not really independent. The probability depends a lot on where we are. For instance, if you're thinking of the Entro Prime lattices where you have the spillover effect that the 761 turns into x plus 1, you're probably happier to force zeros up there, because then you're also reducing the spillover. So it's not exactly the right thing, but it's getting close for the estimates. Bigger solutions, so other multipliers. I had the x plus 1 on the slides before. How hard is it to find those? How likely is it to find those? So that's another interesting question. And then, I mentioned already a few times, this is actually not the right reduction. So the normal reduction for Entro, if it's like atomic polynomial, then it is easier with the rotations. Here you're getting all these extra factors. All right, back to our problems. So we have our problem 2 statement up there. So we have our inhomogeneous solution. We have these equations on the coefficients. And then we also want to reduce our lattice dimension a bit further. So we're taking our ring and just saying, hey, we forget about the ring structure. Well, it's kind of behind because we would be happy with x times a. But let's forget about this for the moment. We want to throw our preferred SAP solver onto this. And so then we have these 761 equations. And then we have another parameter. In addition to the fixing some of the parameters of a to be 0, we now want to project onto something. So we're fixing 600 positions onto which we're projecting. So we're reducing our lattice dimension by another 161. And then we're getting a different rank of this lattice. And so I have my matrix here. And so that just means that I'm cutting out 161 of the equations. So instead of having determinant q to the 761, I am reducing my determinant to only q to the 600, which is nice for the runtime. And, well, it gets smaller. And then I also want to kind of push, because I know that my A is small, I put some extra weight on there, so I do some rescaling. Typical rescaling is such that the these two parts are balanced. So the normal weight in the E part is that I'm having, well, it was this random choice between plus and minus 1. So that gets me the square root of 21, which was larger, square root of the length thing, 2/3 of the length thing, which was 23, which is larger than the 17, which is the average weight, or is the exact weight of our small value over here. So the A, which is guaranteed to be small, this has norm about 17, and the E, on average, has norm 23. And so stuff in the scaling factor, this lambda, and the standard choice is to choose that these balance out. So the weight W, which is what I have in my A, and then the lambda should give me the same 23 that I have in the E part. Is this optimal? It's in the standard analysis. I might want to balance this a little bit, and this is also where it comes in that E might have larger or smaller norm. This is just taking the average norm. But if I think of like weak keys or corner cases, with so many percent of probability, my A will be much shorter or much longer, and it could also be interesting to develop a tech which finds those faster. So there's interaction with the size of this E. All right, last part on this thing. No, sorry, it was the last part on this thing. Now we're getting into the real thing.
Yeah, so there's all these choices in setting up a lattice. And then you throw it over the wall to somebody who's willing to give you short vectors and lattices. Well, they can't find super short, but you ask them to find some as short as they can afford to do. Well, the afford is defined by this beta parameter. There's some BKZ beta. You make beta as big as you can, subject to your time limit, cost limit. And then using that algorithm, you reduce the basis that you had after whatever transformations Tanja was mentioning. And then, well, maybe BKZ is not the best algorithm. There's several different algorithms which all maybe have about the same performance, but just saying, well, yeah, there's some reason to think that they're all kind of similar doesn't mean they're actually similar. But let's ignore that. This is not really a talk about details of choices that you can make at this layer, but do want to emphasize what can go wrong with the analysis. First step of the BKZ part of the standard analysis. So maybe I should say standard analysis, this is what you find in basically all of the NIST submissions. The NIST submissions are following the pattern that we've been talking about, maybe leaving out some of the options like setting up lattices in a more general way than by Galbraith to use the OR module structure. But everybody follows this basic pattern and then does the following. They say BKZ beta will find a vector of about this length. There's some funky formula for delta. And then normally BKZ beta does that. What does normally mean? Nobody wants to say that. They'll say this is the expected length of the vector. Expected? What sort of distribution do you get? It's actually even worse than not knowing like how the distribution is around this length. This formula is wrong. This formula has been repeatedly disproven by every experiment that people have carried out. There's a thesis which is now online where you can find the asymptotic argument for this formula being about right as beta goes to infinity, but there's no bounds. There's nothing saying that, even if you believe the asymptotic, there's nothing saying here's how close delta should get to this beta formula as beta goes up. So what's the right formula? Open question. There's some things called sandpile models where people are trying to develop algorithms which will compute the right delta. And maybe those models are accurate, at least the latest ones saying here's some inaccuracies in the previous ones, but they're also very, very slow. And so nobody uses them to analyze algorithms. And then you keep going on the BKZ analysis. Next thing people say is, well, there's this geometric decrease of the Gram-Schmidt sizes. And well, this assumption, it's kind of about correct based on a bunch of experiments, except that, well, it's not really. When people do experiments and they look closely, then they find, no, you can, every experiment, if you look closely enough, you can detect that the assumption is wrong. It may be not wrong enough to matter, but, well, it's hard to tell. People don't do that analysis. The standard analysis just says, yeah, that's correct, which in turn gives you, via another argument, this is what people call the 2016 estimate, which was shown experimentally to be wrong in 2017, which says if your vector is as small as blah, then you will find it. Sorry?
Citation, please.
For which part?
2017.
Well, let's see, this was Martin, and I'm afraid I don't remember offhand the list of authors. but I mean, you would remember offhand.
Martin, do you confirm you proved that this was wrong?
We thought we confirmed it.
So there are graphs. So I mean, if you look at the graphs in the paper, which report the results of the experiments, then you clearly see that this statement, which is the statement used in the analyses, which says that you find a vector if and only if the length is less than or equal to blah. The experiments show that sometimes when beta satisfies this, when beta is chosen to satisfy this, you do not find the vector. So that contradicts this. Furthermore, sometimes when beta is chosen even a bit larger, you do not find it. That's also shown in the experiments. Furthermore, sometimes when beta is a little smaller, faster attack than the experiments will sometimes find the vector. The same paper has the beginnings of an analysis which explains why this formula is wrong. So I agree that the experiments are saying this is kind of sort of correct, but it's not saying that this is correct. It's saying it's kind of sort of correct. Yeah?
I think that the times where you choose beta following that formula and you don't find them are about 3% of the time or something like that. So it sounds reasonable that on a randomized experiment, sometimes you might get slightly unlucky. I think it's a bit unfair to say that formula is wrong.
Well, this is the statement which is assumed in the standard analysis. And the parenthetical comment here is that the experiments identified deviations from this statement. Now, if you say that the deviations are kind of small, then I agree, depending how you measure them, the deviations are, I mean, the beta that you get out of this analysis, it's probably within a few percent of the right beta. However, consequences of getting this kind of analysis wrong are, for example, that you end up concluding that hybrid attacks are only effective for certain parameter ranges, and that conclusion is not justified. In fact, at the end of the talk, we're going to formulate a theory saying that that conclusion is always wrong. And the reason that people got to that conclusion was exactly this kind of mistake in doing analyses. This is saying there's a sharp wall, and you're saying, well, yeah, it's kind of, sort of around there. Yeah, it seems like it from the experiments. But the experiments clearly show that you don't get such a sharp transition. And exactly that effect is what hybrid attacks can exploit.
I think it's explicit the fact that this is a heuristic, even only because it uses the geometric series assumption, which is by default heuristic. I mean, you could also, if you had a secret or an error that are coming just from a Gaussian distribution, a discrete Gaussian, there is a non-zero probability that your vector is so long that all of these analyses go out of the window.
We agree there's a probabilistic aspect to this. And beyond that, I mean, the argument for this is saying if you take a sort of typical vector and you feed it through certain transformations going through your orthogonalization, then, for instance, in a nearest plane computation, you would see the same thing. Then this is you get some kind of expected size of the result, and you compare that to your geometric series and say, well, yeah, this is when you're going to find things. And I mean, that's sort of a good ballpark estimate. But if you actually want to understand how fast the attacks are, and you want to get, optimize the right things, understand which algorithms are useful speedups, then you have to be more careful with the analysis and not just say, it's if and only if. And I mean, this really is the statement you see in the standard analysis, that you find the vector if and only if the length is less than or equal to that. That is the 2016 statement, and it's just not true.
What kind of analysis do you mean the 2017 paper in particular?
No, but I mean all the NIST competition submissions. I mean,
So all of them have an if and only if sign.
well,
There's
this is the
a-
choice of parameters.
There's a consensus analysis which is used to produce a bunch of numbers which are supposed to be security analyses, and that consensus analysis starts from this statement, which you find, for example, in the 2016 New Hope paper. And this statement is disproven by experiments. And then you can say, well, how far off is it? That's the open question, is to understand how far off this is. So in Wunder's thesis in 2018, there's a pretty clear explanation in the context of nearest plane of why various estimates from 2017, 2016, et cetera, are wrong. And he has a better formula which seems very plausible. And if you adapt that from the nearest plane context to this context, then you get a probabilistic curve which seems to match the experiments. And that's also, again, the beginnings of that are in this 2017 paper. But that still doesn't mean that that's right. It's sort of, it's at least not obviously wrong.
I mean, Thomas was one of the co-authors of the 2017 paper, and he did exactly that analysis for this 2017 paper. And our conclusion was, like, as the block size increases, like, that effect becomes less and less significant. You're talking about the lifting probability in the end, right?
So everybody agrees it's in the right ballpark. That's not the point of dispute. The point of dispute is this overly precise statement, which then leads people to make incorrect conclusions about, for example, hybrid attacks. And the open question is to get it right. And I totally agree that the 2017 paper, and then in more detail the 2018 thesis from him, is saying what feels like the right analysis. I mean, there's, you know, it's not that, it's not he's claiming a theorem, but I mean, the formula seems plausible. But that doesn't mean that this question is solidly answered. It just means that there's a not disproven 2018 thesis on the topic.
My counterclaim would be it becomes more concentrated as you increase beta.
Yes.
Yeah, we saw.
Giving the signal to
Yeah.
To all three
Okay,
speakers.
you only have 5 minutes left. Yeah. So then if you get through all this, the standard analysis then says that, well, you find the vector, the short vector you want, assuming that the lattice transformations that Tanja mentioned didn't throw it away. And if, well, so then you now have this probabilistic thing that maybe worked depending on choices you made in setting up the lattice. And then people say, well, you try it again 1 over p times, where p was the probability of this working. But that's making some independence assumption, which is already disproven in the Silverman paper. It's also implicitly assuming that every time you go through the algorithm, you're choosing the parameters the same, which doesn't make sense if, for instance, E is kind of smaller or larger than you were thinking for your average estimate. Maybe you should be increasing the parameters as you go through, or decreasing, unclear. Or, I mean, just an example of one word in this talk being something that can make a significant difference. There are NIST submissions where if you simply say, wait, it's not divided by p, for quantum algorithms it's divided by square root of p because you can do a Grover search, that makes a 12-bit difference in the security estimates for one of the NIST submissions. So, I mean, these questions, and we made a list of dozens and dozens and dozens of these issues and analyses. In any particular one, maybe it's only 2 or 3 bits getting things wrong, but these things pile up, and it would be good to get them right.
Maybe not even one. I mean, no guarantees. You might not get a paper out of it.
Yeah.
But maybe.
All right, the cost of BKZ, well, the standard analysis says you use sieving, takes exponent 0.292 times beta. This is fake math. It was never justified in the first place. The 0.292 comes from an asymptotic which says 0.292 plus something that converges to 0. Every experiment has said that little o of 1 is something positive. Nobody's sure exactly how it's increasing. I mean, how this expression is increasing with beta. It is reasonably convincing that as beta goes to infinity, the number in front of it converges to 0.292, but that never justified crossing out the little o of 1 and putting in 0. The reason that people choose this particular sieving algorithm rather than enumeration is that they take this fake 0.292 beta number and compare it to an experimental extrapolation from, say, sandpile models, which gives you a 0.187, 1 over 2e, I guess, and then a somewhat harder to explain numbers after that for the cost of enumeration. But if you compare some, even if the extrapolation's right, if you compare that to a fake number, doesn't mean that the algorithm with the fake analysis is faster. Maybe it is, maybe it's not.
So you're saying that things are more secure than as claimed?
It's possible, yes, that, I mean, if you plug in a fake number for your standard analysis, and if nobody can actually write down an algorithm that's that fast, you would guess that the security levels are higher. And then, it can be totally a problem, because if you're telling users your security levels are down here, and what they want is something up here, then they end up taking your system and throwing it away. And then they move to something else, and that something else, maybe you've estimated it badly in a different way. Or maybe they say, this cryptographic stuff is something I can't afford. So it's not that just underestimating security by random amounts for different systems is going to give you a secure cryptographic system. The users have choices of cryptographic systems, and we should be, both intellectually and for the application of crypto, as accurate as possible.
Aren't they described as lower bounds, though?
I'm sorry?
The papers describe the cost as lower bounds.
Depending which paper you look at, there will often be statements saying that the 0.292 is an underestimate, and it's clearly not something that algorithms are going to achieve, which doesn't at all address the issue that I just said of we want to get the right number. The open problem is to get the right number.
I mean, this is the problem you define, but some people might be fine submitting things saying, well, you know, I don't feel perfectly confident in every step of the analysis, so I'm going to take some margin by doing that. And I don't think this is particularly scientifically dishonest.
Did I say that something was dishonest? I was just saying that plugging in some number into this 0.292 when it was never justified. The justification was simply saying, let's just hope that little o of 1 is 0. I mean, it could be that 0.292 is bigger. Saying it's a lower bound suggests to me there's a theorem. Maybe little o of 1 is negative. The experiments don't seem to go that way. But the point is there was never justification for this 0.292, and experiments say it should be something else. So open question is figure out what the right thing is, instead of discarding other algorithms because they seem to be worse than this.
We're waiting for the answer to come. And what do we do in the meantime?
This is a talk which is presenting open questions. And now,
No, this is a talk criticizing everything everyone is trying to do while you're not doing anything on the topic.
this is a talk which is going through a bunch of algorithms and saying, here are open questions regarding the performance of these algorithms. And you seem offended by this.
It says it's a fake number.
This number is fake. Yeah, I mean, this particular one is not a reasonable, I mean, this is scientifically never justified. There's lots of things where people say this is an estimate and we have some justification for it. Like this one, people say how they get to this extrapolation. But this 0.292 is just, I mean, it's fake math. It's really...
I don't understand what's fake about an inequality.
It's not an inequality. It is a guess. It is a speculation that the little o of 1 is, depending what you're looking at, 0 or greater than or equal to 0. It seems from experiments that the statements that it's greater than or equal to 0 are, for the sizes of experiments, justified. But it's really, you know, you can make any number of different formulas which have the same asymptotic as this. And then...
We want to get to hybrids.
Yeah, I was hoping we would get to hybrids instead of dealing with people being offended at their work not being perfect. But... how do we deal with this? Session chair, you are in charge of everything. That's funny.
Just move through this slide so we can show the numbers at least.
Yeah. It's sad to not get to the hybrid, though.
We can keep talking over coffee, too, but...
Okay.
Yeah, I mean, but
So-
there was some actual content which we were hoping to get to beyond...
I think the appeal that we were doing here is please state what you're modeling, please state where you're doing lower bounds, upper bounds, putting stuff to 0 when you're getting a number. So in our submission, we actually ended up putting all numbers in, saying, okay, depending on which model you're doing, these are the best costs we're getting for sieving or for enumeration, depending on whether you're doing hybrid or non-hybrid. And so at least you can say, hey, I have improved your number in the sieving context from this to something else. And so for those, we're saying, okay, here are the estimates and the restrictions we're putting in. And it's mostly an appeal to say, hey, look, when you're putting a O of 1 to 0, say, well, here's the evidence, because we're assuming we're looking at experiments and it seems to be positive. And so we're doing a conservative or underestimate, or as you said, less than equal to statement there. And we're assuming here for the other costs that it's exact, so whatever. So these are our numbers. Now, interestingly is, we went for memory cost and realistic memory cost, where we're saying, okay, well, if you have memory, if you have to pay for your memory, then that was motivating the computational model, and so it gets more expensive. And that hits, for instance, sieving a lot harder than enumeration. For enumeration, we don't see any difference in the cost for memory between free and real, whereas for sieving, it changes the attack levels a lot. Now, columns here, this column here is the pre-quantum. This column here gives you a Grover. And so, for instance, if you have something where you're looking for a collision somewhere, then Grover gives you a square root speed up in those things. And for instance, then you do see in the enumeration context here, in the real memory model, that does get cheaper. And otherwise, there are not so many differences. Then had something prepared for hybrid attacks without quantum computers.
So let's say we skip the slides, but let me just make one comment about it, which is that the lines where you see hybrid attacks apparently not making a difference, like 208 to 208 or 153 to 153. Sometimes they do make a difference. But those, I want you to remember this talk, formulating the theory that those are all calculation errors in the standard analysis. So even with our efforts to correct the various problems, it's only this year that I would say we've identified the error that led to that. It seems that
And that's in our submission. It's not in your submissions. In our submission, we think the hybrid should be faster,
well,
which also means in other
so
submissions.
the theory is that, yeah, I mean, for where we're saying, you know, like, I mean, this one, 208, for instance, not getting faster with hybrid attacks, that appears to be a calculation error from the standard analysis here being more wrong than the standard analysis here. And when that's corrected, then it seems that there's a little bit of a gap. And yes, that would also apply to other submissions. This is, I mean, this is work in progress. It's just an error that we've identified this year. But it could be that every submission is affected by hybrid attacks. Now, that's not confident claim, just theory that we formulated that hybrid attacks always improve the attack picture.
Okay.
All right,
Thanks.
and then we'll skip those slides. So thanks for your attention.
Have a coffee break. I think it's time. So we have one more talk, Christine, at 4 o'clock. You wanted to say something?
I just want to make the comment, if you just remove the word fake and kind of ignore that level of dispute, I mean, it's really a very important point. So it's not just the NIST competition. So homomorphic encryption, standardization is a huge effort. It's a super important technology. We have to get these numbers right. We all know that there's a lot of different options for modeling the cost. And I think like one meta point we could take from this is we just need more work in this direction. So I just want to iterate, reinforce what I see as your global point in this topic.
Thanks.
Okay, so let's take a 20-minute coffee break. We'll resume at 4:05 with the last talk and then the open problem.